Hey nerds, we're checking out three-dimensional vectors today, otherwise known as vectors in space. So here's a little vector in space. Get it? Before we were talking about vectors on a plane, which is just in 2 dimensions, and the vectors have some x component, maybe 3, and some y component, right? Maybe 2, whatever. And we could figure out, so this is the resultant vector. And you could find out its length, you could find out its direction, etc., etc. We're doing the same thing, except now it has one more dimension. It comes not only over and up, but also into or out of the page. So there'd be a third vector that would be, let's get rid of this guy. So now you got a third component to the vector, which is running out of the page. So if you're a artistic-minded person, you could probably see this coming out of the page and getting smaller as it comes towards you. Here's a better image of that. The component vectors in the x, y, and z, but the resultant vector comes as a component of all of that, right? We're doing all the same things. We have I, which is the unit vector in the x direction, right? It goes 1 over in the x direction and none in the others. Y for the j, it only goes 1 over on the y axis, and z k is used to represent the unit vector for z coming into or out of the page. So these are different ways to represent them. Yeah. So you can say this vector OP over here, right? We're going from, let's get rid of all my. We're going from the origin O, right, to this spot P. It goes over some x, over some y, and out some z, right? And so there's our resultant vector. You can also write it in this sort of algebraic sense, where it goes some amount of these x unit vectors. So maybe if this is 3, this would be a 3, and that would mean you'd have 1, 2, 3 unit vectors in the x. If this was a 2, it means you'd have 1, 2 of the unit vectors the same length as these in the y, and etc. in the z. So you'd say 3, 2, and I don't know, whatever, 4, if this was 4, right? Different ways to write it. Fine. Great, so the magnitude of the vector is the same. It's just how far have you traveled in total. And so the length or magnitude, we use the same modulus function or absolute value symbol, right? So you say, what's the length of this vector? Put it in absolute value brackets, and you do the same thing. It's just Pythagorean theorem with an extra component in there, right? So it goes over some distance in the x, over some in the y, over some in the z, square them, add them up, and take the square root. Cool, and that's the distance. Yeah, you're basically you're doing this and finding this length, and then from this length you're doing the same thing again, and square roots, you can do that. You can just compile them into one. So try to find the magnitude of these vectors, sketch them, it doesn't hurt, and pause me until you got them. Go. All right, so here's the vectors on the previous page. They're just made pretty for you. Here's 0, 2, 0. It goes over 2 on the y-axis, right? And so the length of that is 2, right? 2 units. Here's magnitude. You can see that this is only 2 units because it's only 2 units long. If you wanted to be an uber nerd, you'd say the vector A is square root of 0 squared plus 2 squared plus 0 squared. This is 4, and then you take the square root, and surprise, surprise, you get 2. Same thing here. You're just finding you're going over 3, up 2, and altogether you're finding this length. So you're saying the modulus, the distance of vector B, is square root of 3 squared plus 0 squared plus 2 squared, and you crunch all those together. Oh, that should be a 2, sorry. My writing in mouse is not great. And so this is 9, this is 4, so root 13, leave it. I don't need a decimal. Great. And then finally, this vector, I know they kind of make a box out of it, but like it's going 2 over in one direction, 1 over, and then 3 up. So altogether we have this resultant vector. And you can say the modulus, the distance of C, is the root of, can't see it, 2, 1, and 3, right? 2 squared, 1 squared, 3 squared, add them all up, square them, add them all up, take the square root. Magnitude, root 14, great, fine. Moving on. So, yeah, this is vectors between 2 points. So here's our vector, and he's between 2 points. I don't know. So if they give us 2 points, like point P and point Q, you can find the vector to get from one to the next just by, you could plot them in 3-dimensional space and then think about how to get from one to the next. Like P is -3 on the X, so 1, 2, 3. 1 on the Y, 1, and 2 up, 1, 2. So something like that. And Q is 1 on the X, -1 on the Y, and 3 up, something like that, right? Wish you could see this in 3 dimensions. And so that's the vector between them. So they have all of these equations about how to get them with O and B and A, but just like look at how to get, this is the X, this is the X. Look at how to get from one X to the next, right? Here's the Y, here's the Y. How do you get from this Y to that Y, right? Same thing here. Here's the Z, here's the Z. How do you get from this Z to this Z, right? And that's the vector. So this is going from -3 up to 1. So that's what this difference is, right? The change in that. So from -3 up to 1 is a increase of 4, right? And going in the y direction from 1 to -1 is a decrease of 2, and 2 to 3 is an increase in 1. So I think that should be our vector. Oh. 4, -2, 1, great. And here's their subtraction, but you can also just do it visually. You don't necessarily need to write it out. Time is of the essence. All right, great. So that's vectors between 2 points. Here is equality of vectors, and vectors can be equal even if they're not in the same spot on a coordinate grid. So all A and B need to be equivalent is the same magnitude and direction. So A and B, we can figure out that they move in the same way. They're equivalent. They're equal vectors. So let me give you an example of how you might use that. So they say, hey, ABCD is a parallelogram. Great, fine. And they give you ABC, but not D, and they ask you to find the coordinates of D. Well, great. Let's draw it out just so it might help you visualize it. All right. So here's A, B, C, D. I know they're in 3 dimensions, but just to make life easier, we'll kind of put them on 2 dimensions and just represent their X, Y, and Z coordinates with these points. So because it's a parallelogram, vectors love this stuff. It's a parallelogram. If they're parallel, you know that they have the same slope, even if it's in 3 dimensions, and therefore all you need is the same magnitude to say that they're equal. So in ABCD, if this is a parallelogram, then AB should be the same as DC, right? Those should be equal lengths. Sorry, parallelograms have equal sides as well as parallel sides. So because they tell us it's a parallelogram, we do know that these sides should be equal. So I know that this vector from A to B should be the exact same vector as D to C. The exact same meaning the same direction and movement, not necessarily the same spot. Great, so let's figure out what this AB vector is. I know that vector AB really is going from -1 to 2, right? Going from 1 to 2, so that goes over 3. 2 to 0 goes down 2, and 1 to -1 goes down 2. Right? I think that's our vector. So that's how this vector moves, this vector should move in the same way, right? So if we take this, let's see, let me pop to the next page. If we do the same thing with this one, but starting in a different spot, let's pick purple or something. I know we're going to start here, and we're going to take 3, 1, 4, and we're going to add 3 to this component, right? So this should be this 3 plus the 3 that we're moving in the x direction, right? So plus 3. So this piece should be 6. And the b, this piece, right? I know I'm starting here and I'm moving in this way. So 1 minus 2, so this should be 1 plus -2, so -1. And the c should be the z coordinate -2, so 2. Right, so I'm guessing that this is our spot. Try it on the next page. There we go. So they laid it out with a little bit of subtraction, which is fine, but I don't know if it's worth your time. But here's our coordinates for C, and you got there by figuring out how vector AB moved and doing the exact same thing from these points to get to the new point, knowing that DC was the equivalent vector to AB. Great, fine, moving on. All right, and I guess it's not quite lastly, but so now we need to do some operations with vectors in space. Here are some vectors operating on each other in space. It's just getting ridiculous now, so let's get rid of that. So you can do the same rules for vectors as you do for a lot of addition and subtraction. Like addition, we've already looked at in 3 dimensions. You just add the x, y, and z components respectively. You can do the same thing with subtraction. If you want to subtract 2 vectors, just subtract the x, y, and z components. If you're going to multiply by a constant, you multiply the constant by each one of the x, y, and z components. That's fine. If you're adding them in an equation, commutative property works, which means it doesn't matter if you do that vector first and that vector second, right? It doesn't matter which one you do first or second, you'll still get to the same spot, right? Great, so that's commutative property. Same thing with associative property. You can add them in whatever order. The identity property means that if you add nothing to it, you'll get the same thing back. Inverse property means that additive inverse means you add the opposite, you'll get back to where you started from. And a few other things. These are like if you want to know the length of your newly multiplied vector, right? Like you want to know how long 2a is. Well, it's the length of a times 2 times that modulus. And also the distributive property works. Great. You can multiply a, instead of just adding these up, you can distribute the constant in. Great, so let's try those out. Like you to try to solve for x. I'd like you to find the length, if this is a, find the length of 2a, and try to find the location of c and d in coordinates. Think about these ideas, give that a shot. I'll pop back on in a second, go. All right, so with these, the first ones are fairly straightforward. Well, you can just, you can add them or subtract them as normal as you would any other variable. So if we're trying to solve for x, you're getting rid of the r by adding r and adding r. It pops into existence over here. And then you get rid of the 3 by multiplying by 1/3. I know we like to say dividing by 3, it's very safe, but just as a fussy little note, you can't really divide by a scalar. It doesn't really make physical sense to divide by a whole number, but you can take half of something, right? So we multiply by the reciprocal of a scalar. So you never see x is a over 2. You always see x is 1/2 of a or 1/3 of a. It's a proportion of an original length, right? So try to avoid going a over 2 because that doesn't make vector sense. Cool. Same thing here. This is half C minus D, not C minus D over 2. It's a fussy nuance, but they're fussy about it, and I think they'll ding you for it. So I'll try to reflect that. With this, I'm trying to find the length of it. You just find the length of the magnitude of A, which is 14, and then if A is 14, root 14, then twice A is 2 times root 14. Wow. And several ways to find C and D, but 0, 1, 1 and 1, 4, 0 is what I got. What I did was figured out this length and then added or figured out this going from A to B. You increased by 1 in the X, you increased by 3 and decreased by 1 in the Y. Oh, that's this piece. And so I just applied that from this point up and then did it again to find D. They did it here by starting here. They started at the original, and this is just double this vector. So they just added twice the C vector. And this is just 3 times that vector. So they added 3 times. It's more complicated than it needs to be. All right. That's it. I don't always make vector jokes, but when I do, IJK. Get it? Here's your vectors in space, stuff that we're going to attack tomorrow. You don't have to do it right now. We'll mess with them in class, and I'll see you then. Bye.